Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, we'll be diving into intermolecular forces, and we'll learn all about what they are and how they impact different properties associated with molecules. Let's get started. So if you watched the previous video, I started off by just talking about how in order for molecules to be able to go from one phase to another, they had to be able to overcome the intermolecular forces that were present by adjusting the amount of kinetic energy that they had. And we learned that that kinetic energy can be adjusted mainly by changing the temperature associated with the surrounding environment. But now this video, we're really going to be jumping into understanding what are these intermolecular forces, what categories exist, and what molecules have them. All right, so we're going to learn about four main ones and then understand how they impact a variety of different properties along the way. And so the big thing we want to remember is that the strength of these intermolecular forces really determines the physical state of any matter. At room temperature, moderate to strong attractive forces will result in the material being solid or liquid. All right, so make sure you guys earmark that or remember that. We also want to remember that the stronger the intermolecular forces are, the higher certain properties will be, such as your boiling point or your melting point. Now let's think about why that is. If I have very strong attractive forces, strong intermolecular forces, these things are bound, they're holding on to each other tight. And so if they're held on tight, that means I need even more energy pumped in here to get them to ultimately break apart and be able to start moving more freely. And so again, the thing you want to remember, your stronger intermolecular forces, the higher the boiling point or melting point would be. Okay. So there are a number of reasons why different molecules are attracted to each other, okay? And they're listed to you here. And the premise of these intermolecular forces is based on these four things. Well, first, one of the main reasons we know molecules or parts of a molecule can be attracted to one another are through charges, like those that are associated with ions. So a positive ion, a negative ion, those are going to be attracted to each other. And so we understand that. We learned that way back in chapter 2, all right, in chapter 3. But we also have attractive forces that can allow polar molecules to be attracted to each other. The positive region in a polar molecule and the negative region of another polar molecule could be attracted to each other. Now, those aren't permanent fixed charges, but that positive and negative rich and deficient region, those can be attracted to each other. And we even see a special category of this that happens that involves these things called hydrogen bonding or H bonding. And we'll talk about what those are shortly. But even somewhere that you probably aren't even thinking that an attraction would occur happens in nonpolar molecules. Even these nonpolar molecules have these temporary charges that are created or temporary positive and negative regions that are created based on the distribution of the electrons in the molecule. Other things that can impact how strongly something is attracted to each other is the degree of the charge, like how large of a charge it is, +3 versus +1, and then the distance between the different molecules. So again, there are several trends that we're going to explore associated with the strength of these intermolecular forces. And we've already touched on this one. The fact that if I have really strong intermolecular forces, again, those things they're sticking to each other. So those are going to require more energy to separate them. Okay. And so where this impacts things is things like the boiling point or the melting point. Again, remember, the higher the boiling point something is, we can then deduce down that it must have some very strong intermolecular forces. And you've seen this in principle, right? So like if you think about if you spill some water on the table versus if you spill some acetone, some nail polish remover. The acetone, the nail polish, it evaporates really quickly. But the water may linger around for some time. It'll eventually evaporate, but it may linger around for some time. So what we can tell from that, the fact that the acetone can get into the gas phase very easy and the water takes a little bit more time, is that acetone, that nail polish remover, has weaker intermolecular forces than our water. Okay, and we're going to learn about exactly which ones they are shortly. So we're going to touch on 3 of these initially, and then we're going to add a 4th one a few slides down. But these right now, as they're listed, are shown to you in order from weakest to lowest. And so the first type of intermolecular force we're going to discuss is what's known as a dispersion force. Now, dispersion forces are these temporary polar regions that are created in molecules due to this unequal distribution of the electrons. Now, important thing you want to make note about these dispersion forces is that all molecules have them. Whether it's polar or nonpolar or ionic, all molecules have them, okay? All molecules have them. But if we're dealing with nonpolar molecules, those are the ones that don't have uneven distribution of their electrons amongst the molecule. Well, then this will be the primary force that's present, the dispersion, which again, these are our weakest forces because these are temporary charges that are created. We also have what are known as dipole-dipole attractions that are present. Now, these are found in polar compounds. And the reason that these are a bit stronger is because this is a permanent dipole that exists. It's not this temporary fleeting idea that's seen in the dispersion forces. This is actually there. So if you're dealing with a polar molecule will have not only not only dipole-dipole interaction, but also dispersion forces that are present, with dipole-dipole being the strongest. And then the third strongest intermolecular force is what we call H bonding or hydrogen bonding. Now, this is a special category of dipole-dipole interaction that result whenever hydrogen is directly bound to three specific very electronegative atoms. That would be oxygen, nitrogen, and fluorine. When you have that case, that's an even stronger attraction that's created, so even a stronger intermolecular force. Now, we're going to get into all these a little bit more in depth. So again, dispersion forces, these are those forces that exist in all molecules, and they happen because these electrons aren't fixed in space. So as you have different molecules or different entities approaching one another, there's going to be times in which the electrons shift how they're distributed within the molecule. As they shift for temporary purposes, you're going to have a positive region and negative regions created, and then those two entities can be attracted to one another in different molecules. Again, big piece to remember, all molecules have them. And when we're dealing with nonpolar molecules, this is the predominant force that's found. Now, sometimes you may hear these called London dispersion forces, but just dispersion is fine. And so this picture representation is just kind of give you an idea of what's happening to these electrons. So you can see in the various frames here, these electrons are shifting to where they're located in the atom. And then at some point in time, like in frame 3, you end up with a situation where you have more electrons in one region than another. And so that creates a temporary pseudo-negative region, a pseudo-positive region. And then as those encounter other molecules, what's going to cause this almost like cascade effect, where as I approach a molecule with my positive region forward, well, that's going to cause your negative region to shift towards me. And as that negative region shifts towards me, then there's a positive region on the next molecule, and that then causes a shift in the other one. And so this fleeting change in the distribution of these electrons is what's causing the presence of these temporary induced dipoles. Now, some things do impact how much this induced dipole, how effective it is and how strong it is. So one of the things that affects it is the size, like how many electrons are actually present. Well, the more electrons that are present, which coincides with having a larger molar mass, the more electrons that are present, the larger this cloud can be that's going to be shifting one way or the other. As I shift more and more electrons, I'm creating even stronger positive or negative regions, and thus can create more areas for that attraction to occur. So the take-home message in that statement is that the larger the molar mass, the more electrons that it has, the stronger those attractions will be. And if we were dealing with like trying to figure out the boiling point of something, well, then we would say that that molecule with more electrons should have a higher boiling point or higher melting point, respectively. Also, something that can affect this, induced dipole is the shape of the molecule. If you're dealing with something that has a more flat, more exposed surface area to another molecule compared to something that's more stacked and compressed, well, the larger the surface area is, the larger that induced dipole would be, and thus the stronger the attractions and higher certain properties would end up being. And so you'll want to do an assessment of the molecules that you're looking at to determine which one would have the stronger forces. Okay, and you can see some pictures here, just showing the difference of the shape and the size. All right, so again, this really does impact things like the boiling point. So if we look at this series of noble gases here that we know are all in the same column in the same group, as you go down the group, we know we're adding more and more electrons, the molar mass is getting bigger and bigger. Well, look at what's happening with the boiling point. The boiling point is also going bigger, 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 higher, higher, higher. That's because as I go down the periodic table, there's more electrons there that can be shifted, that can create this induced dipole. So it would make sense that as I get further down the periodic table, the more electrons that would be could be shifted and can ultimately then impact the overall boiling point, with that increase happening towards the higher the molar masses. Okay. And we can see this trend holds true in different groups. It's not just isolated to your noble gases. Our group 7s, group 4s, you can see the same trend where as I go down the periods, I actually get a higher and higher and higher boiling point. Okay. We can see that here with this series of alkanes. So this is just a little bit of orgo knowledge for you. The alkane, that alkane definition lets us know we're dealing with these hydrocarbons. So a lot of carbon, a lot of hydrogen, and all of these prefixes that you guys see to the left, the meth, eth, prop, but, all those coincide with a certain number of carbons, and then obviously ties into the number of hydrogens that are there. As I go down this chart, I'm adding more carbons, more hydrogens to this. And so these molecules are getting bigger, bigger, bigger. And so if you pay attention to the columns, the molar masses are increasing. And then so are our boiling points, our melting points, and the densities of these molecules. Okay, again, more electrons, stronger those intermolecular forces, the higher the boiling point, the higher the melting point will be. All right, and we see again this trend here with this series of alkanes. Again, if you see anes, A-N-E-S, that means it's all single bonds. If you see alkenes with the E-N, that means there's some double bonds in there. And alkynes, Y-N-E, that means that there are some triple bonds there. But those prefixes remain the same. All right, and then this here is exploring the impact of shape on these intermolecular forces. So if we look here at these pictures here, we have two molecules that have the same formula, pretty much in the same molar mass. But look at the shape of them. Look at how much surface is being exposed. In the N-pentane example, N meaning just a straight chain, in that example, we have a larger area where this interaction can occur. Versus the neopentane, which has a branch-like structure. Well, in that case, it's a smaller region. So which one do you think would have higher or stronger intermolecular forces? Or let me pose it another way. Which one do you think would have a higher boiling point? So think about it. And so if you said the one on the left, you would be correct. And the reason that is because there are a larger amount of surface area that is exposed for those dipoles to be created. And so you can see, despite having the same exact molar mass, it's the shape that we're looking at to determine which of these would have the higher boiling point. All right. And then the graph is just showing a comparison between N-alkanes and isoalkanes. Again, this is a bit of organic chemistry, but with isoalkanes, those are things that are on branches. And so that's like stacking, like if I have a series of carbon and hydrogen in a line, and then I have a branch of carbons coming off of it. So you can see with our isoalkanes, which now are reducing the surface area of these molecules, there is a decrease in the boiling point, okay? All right, so let's put all this to test. So here we want to choose which of the substances in each of these would have the higher boiling point. All right, so look at letter A. We're comparing CH4 to C4H10. Now, what should be coming to mind is that, well, they're both nonpolar. That's the first question. So if I know I'm doing nonpolar, the main force is this dispersion force. But then we look at, can I distinguish these based off of the molar masses? And yeah, we can tell that C4H10 should be much higher in mass than CH4. And so more electrons. So therefore, we would say that the CH4H10 example should have the higher boiling point. Now, in the second example, where we're dealing with C6H12 and C6H12, we know we can no longer just simply rely on the molar mass to help us to figure this one out, because they have the same molar mass. So what are we going to look at? Well, in this case, we're going to actually look at the surface area that's being exposed. And in this case, the picture may be a bit hard to tell, but the ring structure, that cyclohexane structure, actually has a greater surface area that is being exposed. And so in this case here, we would choose the one on the right in both scenarios as being the one with the higher boiling point. The first one because it has a larger molar mass, and then the second one because there's a greater surface area that is available when it comes to the actual intermolecular forces that induced dipole. All right. All right, so moving on. So that's dispersion forces. Again, all molecules have them, the predominant or main force in nonpolar. All right, now we're going to switch gears to dipole-dipole attraction. So dipole-dipole, if you guys remember from the earlier slide, this happens when we're dealing with polar molecules. Polar molecules have that permanent dipole. They have an uneven distribution. That's there. All right. And so because that's there, you have this positive region and negative region in different molecules that can be attracted to each other. And so because these are permanent dipoles, not these fleeting ones, that makes it a stronger force than our dispersion factors. And so when we're comparing something that is a polar molecule with a similar molar mass to a nonpolar molecule, we would expect that the polar molecule would have a higher boiling point, higher melting point because of those stronger intermolecular forces. All right, and we can see that here. So if we look at formaldehyde versus ethane, again, the molar masses, they're very close to one another, a 0.04 difference, but the structure and the overall polarity of each of these is very different. The formaldehyde is a polar molecule. And I just want to remind you all, when you're declaring something being polar or nonpolar, don't rely on the Lewis structure, which is what we see here. You need to dig back in your bank and think about what is that molecular geometry? And is there symmetric pull? If there's not symmetric pull, then we say it's polar. And we can see here in comparison, our polar molecule has a very much higher boiling and melting point compared to our nonpolar molecule. All right, and we again can see this holding true here, where we have a series of things that all have pretty close molar masses, but look at the difference in those boiling points. In this case, what we're dealing with propane, that very first one, that's a nonpolar molecule, so only dispersion factor forces there. But then when we get to this dimethyl ether, now that's a more polar molecule. So again, notice the boiling points going up. When we get to the acetaldehyde, that one now, again, a much more significant jump because you're more polar with that carbonyl group. The aldehyde group. And then the acetonitrile is even higher in the boiling point because of that dipole moment being so great. All right, so again, having that permanent dipole does make it more likely to have a higher boiling point. All right, so let's put what we know into motion here and test our knowledge. So this says determine if dipole-dipole attractions occur in CH2Cl2 molecules. Well, go through that progression. We have to actually take ourselves back to chapter 9 and 10 before we can answer this question. All right, so what we're going to want to do is come up with our Lewis structure. What does the Lewis structure of this molecule look like? And then determine the electron geometry and the molecular geometry, and ultimately determine the polarity of the molecule. Once we know if the polarity, then we can make declaration of, well, should these types of intermolecular forces be present? All right, and so if you are drawing it out, you should have got a Lewis structure that looks similar to this, where we've placed carbon in the center. It's the least electronegative atom, and then we put hydrogen and chlorine external to it. When we look at that, we see 0 lone pairs, 4 bonding regions. So that tells me that the electron geometry would end up being tetrahedral. There are no lone pairs, so that also tells me that the molecular geometry is also tetrahedral. And because all the atoms on that central atom are not the same, I know there's unsymmetrical pull. And so I would expect that this should be a polar molecule. And so if I'm saying that this is a polar molecule, then I would expect that, yes, indeed, there should be dipole-dipole forces here, in addition to dispersion forces. Remember, all molecules have those. Okay. All right, so here it says, choose the substance in each pair with the higher boiling point. And so look at letter A. Again, very similar formula, just the placement of those fluorines is different. And so what you should be noticing is those fluorines. In the first example, the fluorines are opposite to one another, versus the second one, they're on the same side. So which one is going to impact the polarity more? Well, you should be saying the second one, the one on the right, because now I have this greater pull that's happening on that side of the molecule. So because it's more polar, I would expect stronger intermolecular forces. So therefore, it should be the higher boiling point, the one on the right. In letter B, same thing. We're looking at those chlorines or those functional groups. Where are they at? And so our chlorines in this case are on either the same side of the double bond, and that's why that cis declaration is there, or they're on opposite sides of the double bond, and that's why the trans declaration is there. And so similarly to the first example, the one that has those chlorines on one side, well, that's pulling a lot more. And so because we have that uneven pull, we would expect that the cis version would have stronger intermolecular forces and thus be higher in boiling point. Okay. And so these should be the selections that you are making for this compound. All right. All right. All right, moving on to our third intermolecular force, and that is hydrogen bonding. So hydrogen bonding occurs in polar molecules. So let's start there. You have to have a polar molecule. But then in this polar molecule, you also have to have hydrogen that is directly bound. Notice what I'm saying, directly bound to a very electronegative atom. If you have a polar molecule with hydrogen directly bound to oxygen, nitrogen, or fluorine, well, then you have a molecule that can also not only do dipole-dipole and dispersion, but now can do hydrogen bonding as well. And this happens because you remember hydrogen only has that one electron. And so if it's coupled with a really electronegative atom, well, it's essentially almost being de-shielded. There's, the electrons being taken away. With it holding on very lightly. And so that creates a very, very strong positive region for these attractions to occur. And so you can see this in a molecule like HF. And incidentally, this is the only molecule that involves fluorine that will involve hydrogen bonding. Any other time that you have fluorine and hydrogen in another molecule where there's like more carbon and hydrogen, whatever, then you don't have hydrogen bonding, because remember, fluorine can only make one connection, can only make a bond with one thing. And so this is the only example that involves fluorine for hydrogen bonding. For oxygen and nitrogen, there's a ton of examples, but for this, it's the only example, okay? But you see that positive and negative region being attracted to each other. This is something that is present in water. And notice water has two places where the hydrogen bonding is occurring. So that makes water really strong, has really high intermolecular forces here. Okay. And then again, hydrogen bonding, they're very strong compared to dipole or dispersion. And this does really push up those boiling points. Remember, earlier on, I mentioned this idea about water versus acetone, and water boiling at 100 degrees, whereas acetone can evaporate at room temperature. And so you can see that it does significantly impact your boiling and your melting point. But I do want to clarify, while I'm saying these are strong, they're still not as strong as an actual chemical bond. It only makes up about 2 to 5% of the actual strength of a covalent bond. Okay. Now here we can see the effect of hydrogen bonding on boiling points. So again, we're looking at things that have they're identical formulas, same number of atoms that are present, same molar mass, but the difference is in our ethanol example versus dimethyl ether. Ethanol has that OH, that hydroxyl group coupled to it. And so you can have hydrogen bonding occur. And so look at the boiling point, very drastic difference boiling point. 78.3 versus negative 22 for that dimethyl ether. And then you can see this is a really great graph that shows how the molecules that can do hydrogen bonding stand up to those that are in its group. And so you can see in the example of like H2O, HF, and H3 that are all compared to their counterparts in their group, they have higher boiling points because those three can all do hydrogen bonding. But notice CH4 is not higher because it does not do those intermolecular force, those hydrogen bonding. And so you see its trend holds true with what we would expect moving down the periodic table. Okay. All right, so let's put all this to motion. So it says one of these compounds would be liquid at room temperature and the others would be gases. Which one and why? All right, so do a quick survey of each of these and let's think about it. And so, what you should be doing is not only looking at these Lewis structures, but also think about those electron geometries, molecular geometries. Is this a polar or non-polar molecule? And so as we do that for your formaldehyde, we know formaldehyde is a polar molecule. There would be dispersion forces there because that's in everybody. It would have dipole-dipole interaction because it is a polar molecule, and there is no hydrogen bonding present. And I know you're like, well, wait, there's hydrogen, there's oxygen. Why isn't it hydrogen bonding? Well, that hydrogen is not directly connected to the oxygen. So because that's the case, there is no hydrogen bonding present. Okay, so moderate intermolecular force is found there. All right. And so if we look at fluoromethane, well, fluoromethane, again, would be tetrahedral in shape, but it would also be polar because of that fluorine. So we do have dispersion forces because it's in everybody. We have dipole-dipole because it is very polar. But again, we have no hydrogen bonding because that fluorine is not directly connected to the hydrogen. Okay. And then hydrogen peroxide, we know would have dispersion because everybody got them. It would be dipole-dipole interaction because it is polar. But now in this case, we do have the presence of hydrogen bonding. So because we have the presence of hydrogen bonding, that tells us that indeed this would have the highest intermolecular forces or strongest. So we would expect, remember, the stronger the intermolecular forces are, the more likely it will be solid or liquid at room temperature. And so with having all that in mind, once you've compared all of your intermolecular forces, we can then make a decision. And so out of all these, they all have very similar molar masses, but the one that stands out is the hydrogen peroxide. It can do hydrogen bonding. And so because it can do hydrogen bonding, we would anticipate that it should be the strongest, and we would then predict it to be our liquid, okay? And so that's how we would break that down. We could also do direct comparison, trying to predict which of these would be liquid at room temperature. Again, if we look at our methanol example versus CH3, CHF2, again, think about what the actual structure looks like. Is this polar, non-polar? And so while they're both polar, your methanol has hydrogen bonding. And so we would expect that to be our liquid, the one on the left. And then the one in letter B, when we look at the one on the left versus the one on the right, again, draw out the structure, we'll see that that hydrogen is not directly connected to that oxygen, but it is directly connected to the nitrogen in the second example. So we would expect that because it can do hydrogen bonding, that it would have the ability to be a liquid at room temperature. Okay. All right, one more. All right, the last intermolecular force that we're going to deal with is our ion-dipole attraction. Now, this happens when we're dealing with a mixture of ions from an ionic compound that are attracted to the dipole parts of a polar molecule. So think like salt and water. This is why salt and water can blend. The strength of the ion-dipole attraction is one of the main factors that allows us to have these soluble ionic compounds in water, where you end up with the anion region, the negative region, being attracted to the positive portions of your polar molecule, and the cation being attracted to the negative regions of your polar molecule. So again, this is ion-dipole. And so here, again, solubility is impacted by these intermolecular forces. We might say that our CH3OH compared to CH3CHF, well, that solubility piece, what we're really looking for is similar intermolecular forces. So because letter A, the one on the left, can have hydrogen bonding, it's more similar to our water. So we would anticipate that it would be soluble in the water. In letter B, where we have this pentane on the left and CH3Cl on the right, well, the pentane is nonpolar. Dispersion is the main force. CH3Cl is polar. It doesn't do hydrogen bonding, but it is polar. And so because water is polar, we would expect that it would be able to dissolve in there, okay? All right, so to summarize everything we just covered, remember that dispersion forces are your weakest forces that are out there, and all molecules have these. The magnitude of the dispersion forces does increase with the molar mass. Our polar molecules, in addition to having dispersion forces, also have dipole-dipole attractive forces. And then there's a special category of dipole-dipole that exists called hydrogen bonding, and that happens when you're dealing with hydrogen directly bound to oxygen, nitrogen, or fluorine. And then you have your ion-dipole, which is the result of having ionic compounds bound with polar molecules. And this is going to be your strongest intermolecular force. And just remember that all of these intermolecular forces dictate the ability for things to be soluble in one another. And we're going to dive into that a lot more in another video. And so this is a really great summary slide for you. If you look at nothing else from this video, this is the slide that you want to look at because it lists all of your intermolecular forces in order from weakest to lowest. It has great visual aids for you. I hope this video helped you guys understand intermolecular forces, how to spot them, and how to make some categorize things based off of them and make predictions. Make sure you guys like, comment, and subscribe, and let me know what other material you'd like to see. And I'll be back with more videos in the future. Have a great day. Talk to you later. See you later.